currently we have detected thousands of exoplanets orbiting other stars using the transit method, which is when a planet passes in front of the star and it blocks out some of the light, and we then can detect an exoplanet. However, we're really struggling to detect exomoons. I mean, part of that problem is they're very small in comparison to the planet, so they're going to be very difficult to detect. But one of the methods that we can use is transit depth variations, which we'll have a look at in this particular video. So, for a single exoplanet, we would expect a symmetrical transit. So as it passes in front of that star, it blocks out the light from the star in a fairly symmetrical U-shape pattern. So as it goes in front, we get this typical shape. And if it's got moons or ring systems around it, then we wouldn't expect it not to be symmetrical. But for a single exoplanet on its own, we get this typical U-shape transit. Now, when you look at multiple transits, so if it's got an orbital period of, 10 days, every 10 days we're going to get a transit, and it should be relatively similar. So if it's a single exoplanet there with no other planets in the system, it should be pretty much the same each time. And in the context of this video, the depth of the transit, or the amount of light that it blocks out, shouldn't change each time. So it should be fairly consistent. That transit depth shouldn't really change. So, if you have an exomoon orbiting the exoplanet, well, then it's not really orbiting the exoplanet, they're orbiting a common centre of mass. So the exoplanet itself is on a small orbit, and then the exomoon is going around as well. So you've got this kind of system here once you then introduce one of these exomoons. And every time it passes in front of that star, we will see it in a slightly different configuration. So the exomoon and the exoplanet, they're orbiting their common centre of mass. That is then orbiting around the star. And it doesn't necessarily mean that the orbital period of the planet-moon system is going to be the same as the planet going around the star. So each time we see it, it's going to be in a slightly different configuration, so different orientations. It might mean that the planet passes in front of the star first, or maybe the exomoon does. And this is quite important when we start to look at the transit shape and variations in that when we look at each one. So, one video we had a look at a while ago was an asymmetric transit for detecting an exomoon. So what happens here is, as I mentioned then, the exoplanet may lead first, followed by the exomoon. So at the top there you've got the transit, and it looks different to the other two. So what's happening there is the exomoon, so the exoplanet is actually blocking the light out first, and then when that exomoon follows as well, you've got the light being blocked out by both objects. Then the planet passes past the other side of the star, and you're left with just the exomoon. So you get this asymmetric transit where it blocks out some light, then a little bit more light, and then very little light as you're left with a smaller exomoon. Now, if it's in the other configuration, so the exomoon goes first, then you get a little bit of light blocked out first, followed by the combination of both of them, so both together, and then just the exoplanet. So again, you get the transit looks like it's been flipped. So you get this asymmetric transit, and that can help identify if there's a moon there, for example. So again, an asymmetric transit is going to hint towards a system that may harbour a moon there. However, when we consider that, it's likely that the moon is orbiting in the same plane as the planet. So the planet orbits the star on this orbit, and then the moon is likely going to be in the same sort of plane, the same orientation, so it's orbiting in the same direction. That's if it's formed together. So most of our moons in our system, they are what we would call like prograde ones. So they're orbiting the same direction that the planet rotates and the same direction that the planet orbits the star. But if it's inclined to that orbit, so it would look exactly like this. So the orbits are kind of going this way whilst the planet is orbiting in a straight line. So as it passes in front of the star, you're looking at that and the orbits are going that way, which is important for the transit depth variation, or the depth of the transit, and varying each time round. Because not only is the planet going to lead first, exit, and it's going to change the orientation, it's going to pass across the star at a different location. So it may actually pass across the top, or it may pass more across the center. Now that is interesting because that then relates to things like the inclination of the orbit, which is it relates to the shape of the transit essentially, and it can be more V-shaped or more U-shaped depending on the inclination of the orbit of that planet. And it relates to the impact parameter. So if it transits towards the top of the star, it has an impact parameter of 1. If it transits more across the center, then it has an impact parameter of 0. So what does that actually mean for the transit? Well, we have this thing called limb darkening. So towards the edge of the star, towards the limb, it's dimmer. So the center of the star is the brightest. So if it passes across the center, it will block out the most light. So here we've got an example where that planet is passing across the center and it blocks out the most light. So you've got the deepest transit there. Now, if it passes across the top, then it's going to block out the least amount of light because it's going across the limb and it's dimmer across that part. So it actually blocks out less light. So your transit has a much shallower depth to it than if it was across the center. And if you've got that moon orbiting, then the planet is essentially on a small orbit as well. So it's going to orbit up and down. And it only really relates to planets that are inclined compared to, also the moon orbit compared to the orbit of the planet around the star, I should say. So what you would then do is you would look for multiple transits. So you can't really detect this with one transit. You would need to get multiple transits across the star and look for variations on that. And if you can basically find any variations in the depth of that, it could suggest that there's an unseen exomoon there orbiting the planet, because we're unlikely to detect directly these exomoons because they're quite small in comparison to the planets. The planets themselves are quite hard to detect. But if we can look for variations in the depth of that planet, it could hint to a moon being there that we can't actually see. Now, it only really works if it's inclined, like we mentioned. So let's say it's 90 degrees to the actual orbit of the planet around the star. This would be similar to Uranus and its moons, which is knocked over almost 90 degrees, but it wouldn't work necessarily for planets which are in the same, or the orbits of the moons are in the same plane as the orbit of the planet. So you're looking for ones that are kind of knocked over. Or it could be that the moon is captured. It's a large captured moon which might have an orbit in a different direction. So it's a fairly specific case, this one, but it could be a technique used to look for exomoons in the future. Thank you for watching, and if you enjoy, then check out some of the other videos.